One way of representing an inverse is to think about inverse operations. For example, if we had x plus 3 equals 9 and we had to solve for x, what would we do? We'd have to subtract 3 from both sides. So what would happen is that we would end up with x by itself. So x is equal to 6 here. The same thing applies to functions. Just like how adding 3 is the inverse of subtracting 3, suppose we had a function f of x equals x plus 3, and we compared it to another function, g of x equals x minus 3. It turns out that these functions are inverses of each other, which brings us to another way that we can define the inverse of a function. The way that we define the inverse of a function is that when we compose the functions, something special happens. So suppose we take the function f of x and we put the function g of x inside of it. Remember that the function f of x is just basically add 3. So whatever we input, we have to add 3. So if we're inputting x, we have to add 3 to that. So if we input g of x, we have to add 3 to that as well. But remember that g of x is x minus 3. So we're doing x minus 3. So what would happen here? If we had minus 3 and plus 3, if we subtract 3 and then add 3, they would cancel each other out. So we would just have x. In other words, f of g of x, in this case, would just give us x. What about if we compose the function the opposite direction? So suppose we did g of f of x. In other words, g would be our outside function. Notice that g, all we're doing with the function g is that we're subtracting 3. So whatever we input, we have to subtract 3. In this case, we're inputting f of x. Remember that f of x is all of this right here, x plus 3. So we put x plus 3 there. So if we add 3, then we subtract 3, what happens? We just end up with x. So in other words, g of f of x is equal to x. So basically, with inverse functions, whenever we compose them, we always just end up with x. So now we can ask the question, if you have a function, how do you find the inverse of that function? So suppose we had the function f of x equals 3x plus 5, and we needed to find the inverse of the function. Well, the inverse has to do the opposite. Notice that we're multiplying by 3 here. So in our inverse function, we would have to be dividing by 3. Notice also that we are adding 5. So in our inverse function, we have to subtract 5. And we need to make sure the order is correct. One way we can actually come up with the inverse of a function is by following the following steps. First, we're going to replace f of x with y. So this function can be rewritten as y equals 3x plus 5. Then we're going to switch the locations of the x and the y. So y and x are going to switch places. So we would rewrite everything as x equals 3y plus 5. Now let's try and get y by itself. What would we need to do here? We'd have to, first of all, subtract 5 from both sides of our equal sign. We would end up with x minus 5 on the left and 3y on the right. Now we have to divide both sides by 3, and we get y by itself. So in other words, our new function says that we're doing x minus 5 first and then dividing by 3, which is exactly what we said should happen. Notice that this new function does exactly what we said that it should. We're dividing by 3 and we're also subtracting 5. Suppose that we're given the function f of x equals square root of x, and we're asked to find the inverse of that, we would need to replace, first of all, the f of x with y. So it would become y equals square root of x. Next, we would switch the x and the y, so it would become x equals square root of y. How do we get the y by itself, though? We'd have to undo the square root. So we would end up squaring both sides. So if we square a square root, it eliminates it. So now we would just end up with y. On the other side, we have x squared. So our new function, our inverse function, is y equals x squared. Sometimes we can represent it as an entirely different letter name. So we could say g of x equals x squared would be the inverse of f of x equals square root of x. But sometimes the same function can be rewritten with just a -1 at the top. That -1 is not a power. That -1 means the inverse. So we can read this as f inverse of x is equal to x squared. All this means is that the inverse of our original function is equal to x squared. There's an observation that we can make as well. If we look at both functions where they share a common domain, which is in quadrant 1, do you notice what happens here? This function is symmetric with respect to this function along a particular line. So, in other words, they're both symmetric with respect to this line. And this line is essentially y equals x. So one thing that we know is that inverse functions, if two functions are inverses of each other, they're always going to be symmetric with respect to the line y equals x.